Hi guys, I want to give you a little bit of feedback on your work that was due on the 26th. The first thing I want to do is I want to talk about your pivot lab where you were looking at the balls that were accelerating. All of these balls should have, except for a styrofoam ball, which is affected by air resistance more easily, all of these should be accelerating around or very close to 9.8 meters per second every second. Because once they leave the hands of the people that are throwing them, the only force that's acting on them is their weight, the force due to gravity. And that means that regardless of their mass, their weight will be enough, will pull on them enough to make them slow down and speed up by 9.8 meters per second every second. Because that's just the way it is on Earth. If we went to the moon, gravity would be 1.6 meters per second every second. Now, what you have to do to collect data for this is you have to fast forward it until the balls are not touching a hand. And then take note of the same place of the ball at every instant in time. So what I did is I turned on the measurement tool and I used the bottom of the ball. And I just, at 0.0866667 seconds, that was my time in seconds, I wrote down that this was at negative 63 centimeters. And then I fast forwarded it a couple of seconds. Then the green ball was at negative 55 centimeters at 0.107333 seconds. And I just kept doing it, taking data points until the ball gets to its very highest point and then on the way down. Okay, so you want to keep doing that until the ball rises all the way up to the top and all the way down, back down. So you get some motion before and after. Now, when you're done, you're going to have a graph of time versus position. You can also calculate the speed that it was traveling at, and you could have added some speed columns. If you did the position graph, and what I'm going to do if I did the position graph, then let's say I want to do it for the green ball, then I would do the y of that ball, and that would be on the y-axis, and time. The position is going to be a parabola. Now, a position graph that's a parabola means the ball is accelerating. So you're asked to describe its motion. It's either at rest, traveling at constant speed, or getting faster and faster and changing direction, which is acceleration. So those were your three types of motion that you could describe. And in this case, it's slowing down and then speeding up, and it changes direction. So it is accelerating, and it is undergoing constant acceleration because when I look at this graph, it's a parabola. If I do a curve fit, I'm going to do a y equals ax squared fit. Oops. Wait a minute. No, I'm not. I'm going to do a quadratic on it because it's a quadratic equation. And I'm going to see that this formula right here, this is the same formula as our kinematics equation that says x equals 1/2 t squared plus vit plus some constant. A is 1/2 of our acceleration. So if I want to know what the acceleration is of this, it's twice A. Now, I could have created a velocity graph. So I would have to calculate my velocities, and if I did that, I would calculate my velocities, and instead of putting position on the y-axis, I put velocity on the y-axis. And if I do that, then I get a line because my velocity is changing at a constant rate every instant in time. On the way up, when I have positive velocities, I'm decreasing by 9.8 every instant in time. And on the way down, I'm increasing by 9.8 every instant in time. So if I do a curve fit for this, I'm going to do a curve fit for a line. And I will find that the slope of this is centimeters per second, or centimeters per second squared. And the slope is negative 981 or negative 9.8 meters per second squared, which should be gravity. It doesn't matter which ball, except for the styrofoam ball that I do the data for, I should find gravity to be very, very similar. Okay, it should be very, very similar to 9.8, very close to it, barring some measurement errors with the video analysis. Because on Earth, gravity is 9.8 meters per second, or 980 centimeters per second every second. That's how much we change. So you should, if you're asked to compare gravity on the balls, you should graph another set of data. And that's what was done here. You should graph another set of data. If you don't graph another set of data, then and look at the slope of the velocity or look at twice the A coefficient of the position graph to kind of compare those numbers, then you don't really know for sure if mass is affecting things or not. But mass should not really affect anything. What does affect it are outside forces. And so styrofoam ball is got all these little holes. It's really, really light. And it turns out that air drag affects it more easily than it does other the more solid spheres. So what happens is, as that styrofoam ball starts to rise, it is actually being slowed down even more by air drag and is affected more easily. So it's not because of its mass, it's because air drag just affects it more easily because it is just really light, and just a little bit of air can cause it to have problems. So if you did not make 100, you can get this and you can redo it. I've set it so that you can redo it. You need to redo it by the next due date. The other thing I want to talk about is your homework. And I want to make sure that you understand how important it is for you to read the directions. I want you to make sure that you understand what polar directions are. So polar directions are measured from the positive x-axis. So if I were to do a search for that on Google, I'm just going to show you. I would be measuring that angle from the positive x-axis. Okay, so if I measure an angle pointing east is 0 degrees, north is 90 degrees, west is 180 degrees, and south is 270 degrees. So when I use tan theta, if I'm in the first quadrant, tan theta is just whatever angle I get. And that's my polar heading. But if I'm in the second quadrant over here, I'm actually finding the complement to that angle. And so I want to subtract that angle off of 180, and that'll give me my polar heading. If I'm in the third quadrant and I use tan theta, I'm finding the complement. And so I want to add that to 180, and that'll give me the total angle all the way over to where it is. And in the fourth quadrant, I subtract the angle I find with tan theta from 360. So you'll need to review that, and that's in the math review in your book. So you want to make sure that you review polar angles, because that's how we give directions. The other thing I want to mention to you is that, I like it when you show your work. So make sure you're showing your work. And this was a fine way to do it. And I wanted to make sure that you understood that you need to show your units and you need to round to 3 sig digs, which this person did. And you need to use complete sentences when necessary. So I've posted this solution in your module section so that if you want to look at your answers again and just take a double look at them, make sure you've got the same thing, that you can. But this is what I'm looking for. Okay. All right. If you have questions about your homework, please let me know and I'll be glad to meet with you. I really don't mind meeting with you. I want to help you, so please let me help you if I can.